All right, it is 2:30. We're going to go ahead and get started. Welcome to week 3 of Advanced Kentucky's AP content review sessions online for Calculus BC. My name is Aaron Timmons. I'm the Mathematics Content Director. I'm joined by Michael Marshall, former AP exam reader for Calculus AB and BC. He's our current Access to Algebra Program Manager or Content Manager. And then also our presenter for today, Mr. Mark Howell from Gonzaga College High School. So we're extremely privileged and lucky to have him here today. He's going to talk all things sequences and series with you for the AP exam. So before we get started, just go over a couple housekeeping items here. This review session is intended for a Kentucky audience. However, we welcome students from all across the world. We'll do all we can to provide every student with an equitable opportunity to learn. During the session, we encourage participation, but if you are causing a disruption, you will be removed. Our contact information can be found on this page. If you need to email Michael or myself afterwards, feel free to do that. Give us a follow on Twitter. Check out our Facebook. We'll be happy to get back to you. During the entire session, your microphones are going to be muted, and we ask that you leave your videos off. If you turn your videos on, you'll be removed. Please utilize the chat feature in the bottom right-hand corner of your Zoom screen. Any question for the group, teacher-student questions, I know we have some teachers in here. Please feel free to ask those to any of the three of us. We will make sure to get some answers for you. Michael and I will be monitoring the chat room. If you prefer to send us a direct question, you can do that as well. But I know that sometimes we want to post questions to the entire group. Please check out kyap2020.com. This is where today's recording, as well as all previous recordings, will be posted. You can also find additional resources for both teachers and students here at this website. So before we go any further, I'm going to pause the recording for maybe 2-3 minutes here, let you get situated. Please make sure you have today's handouts pulled up. And if you can open up another browser and go to this bit.ly link here just to sign in. It's a very quick 4 or 5 question Google form. Take some time, fill that out, get situated. In about 3 minutes, I'm going to resume and we'll turn it over to Mark. So please go ahead and take some time here. If you have questions, put them in the chat, make sure everything's working, and we will see you here in a second.
And welcome everybody. My name is Mark Howell, and as Aaron said, I teach at Gonzaga High School in Washington, D.C. I've been teaching AP Calculus there since it seems like time immemorial. More than 30 years, more than 40 years, actually. And I'm delighted to be with you. I'm honored to have been asked by Advanced Kentucky to do this session with you, especially since the topics that we're going to be talking about, if I were a betting man, I would say that of those 2 free response questions that you're going to see on this year's AP exam, I would bet that you will see at least some parts of one of those questions, at least, will involve these topics from today. Almost, in my mind, a 100% chance that that's going to happen. So, and fortunately for you, the students that are getting prepared for this, fortunately, they've trimmed down the content from Unit 10, where all of this is taken from. And I'm going to show you to start with exactly what that content is that you should expect to see. So really, we're going to this is really 2 sessions in one, frankly, because the stuff that's in Unit 10 really does, it really does come under 2 discrete sorts of kinds of topics. On the one hand, we're going to be talking about convergence of infinite series. And under the topic of convergence of infinite series, you're going to see these 4 tests for convergence potentially assessed. The geometric series test, the harmonic and p-series test, the alternating series test, and the ratio test. Those are the only ones you have to know. There's others that you may have covered, your teachers may have done with you, you may have seen before, including the nth term test, the integral test, the direct and limit comparison test, tests for absolute versus conditional convergence, and so on. None of that stuff, and none of the stuff about like error bounds, either alternating series error bound or Lagrange error bound, will be assessed. It says here that the definition of convergent and divergent infinite series will not be tested, and I think that's true, but it's really important that you understand the difference between what it means to have a convergent series and a divergent series, right? What does it mean to say the series 1 + 2 + 3 + 4 on forever diverges as compared with the series 1 plus a half plus a fourth plus an eighth plus a 16th on forever like that. That latter series, actually, if you add all infinitely terms, you get a finite number, whereas the former series will just, the partial sums will decrease to infinity. Just understanding the nature of convergence and divergence is an important thing to understand. So what are the things that you have to be able to do? Those are the things that you have to know about. What are you going to have to do with them? And that's what this slide is meant to convey to you. You should recognize various types of series, and then having recognized what type of series is in front of your eye, be able to apply a test that will tell you whether that series converges or not. If you have a geometric series, not only will you have to determine whether or not that series converges, but in the event that it does converge, what it converges to. And that's a unique feature this year of the geometric series. I think that's the only one that you might have to know what a series converges to. You should understand that an infinite series converges to a real number if and only if its sequence of partial sums exists and equals the sum. Well, that actually won't be assessed. But again, the understanding, that actually is getting to the definition that I spoke of a moment ago. That won't be assessed, but understanding that fact, I think, is still important. And then finally, using these methods, applying these methods to test for convergence from those 4 that I mentioned: geometric series, p-series tests, the ratio test, and the alternating series test. Being able to apply those, okay, will be definitely stuff that's going to be assessed. Okay, so here's what we're going to do for the rest of this time. Okay, so I have an introductory activity that'll be applying the conditions, looking at the conditions for those 4 types of convergence tests. We'll look at multiple choice questions. We'll look at free response questions. Then we're going to move on and do kind of the same thing in the context of the other big topic for today, which is the topic of Taylor polynomials. And so what I have here is a very short little table for you to at least think about filling in those blue rectangles. So at the end of your handout, there should be a page towards the end where you have a summary of all of the convergence tests. There'll be information there that'll help you to fill in these rectangles. So take a minute and go ahead and fill these things in. I'm going to give you a minute to look those things up. And in these, for three cases, you can fill these things in. And I hope that it was clear that when I said earlier that the nth term test will not be assessed. So that means that the stuff in this first row, this stuff here, you actually won't have to worry about for the AP exam. But go ahead and see if you can look it up anyway and fill this in, and I'll give you a minute to finish that. And then in a moment, I'll just show you what these things, how these things should have been filled in. And then we'll do the same thing for the other tests, the ratio test and the alternating series test. So I'm going to go ahead and pull these answers up. So the only way that a series can converge, has a chance of converging, is if the limit at infinity of the nth term is 0. So if the limit of the nth term of a series is anything but 0, the series diverges for sure. And that should just make sense to you, although that test will not be required on the exam this year. It's such a fundamental test, though, that I thought that it would be appropriate to include it here. You'll need it for the rest of your life, if not for the May exam, if that's when you take it. The geometric series, of course, a geometric series converges if and only if the common ratio, R, the constant common ratio, is in absolute value less than 1. A geometric series diverges if the common ratio, the absolute value of R, the absolute value of the common ratio, is greater than or equal to 1. And then a p-series is defined to be sigma 1 over n to the p, like 1 over n squared, p would be 2, and that series converges whenever p is greater than 1, and diverges if p is a positive number and anything less than or equal to 1. And by the way, if p is a negative number, you will still have a divergent series. I mean, if p was like a -3, we would have 1 over n to the -3. That would be the sum of n cubed, which definitely diverges also. But we wouldn't call that a p series by definition. So here's another one of these, a couple more of the other tests. Again, I'm going to give you a minute to fill in the blue boxes. The same information, the same page in the back, that reference page, will have answers to these things. See if you can figure out what will go in these 5 blue boxes that cover these 2 tests. And by the way, in that last column where they have comments here, the first one for the ratio test is important. The second one, that error bound stuff, you won't need to know about that stuff for the exam. Error bounds are not going to be tested on this year's exam. So the alternating series error bound will not be tested. So here's the answers to these. By the way, notice how the ratio test is very similar to the geometric series test. In fact, a friend of mine explained that, why that was made sense to me some years ago when I was wondering about why the ratio test was true. And he said, well, just think about the ratio of the n plus first to the nth term in the same way you think about it in geometric series. That's what R is. It's the ratio of the n plus first to the nth term. It's just constant in a geometric series. Well, the idea of the ratio test is if out infinity that ratio is a constant less than 1, then the series converges. And if it's a constant bigger than 1, the series diverges. The way the ratio test is different from the geometric series test is if that ratio is equal to 1, the ratio test is inconclusive. But for a geometric series, when the common ratio, the constant ratio, is equal to 1, you definitely have a divergent series. Okay. And then the 3 conditions for the alternating series test: you need to first have an alternating series. You need to have the terms have to decrease in magnitude. That is, the absolute value of the n plus first term has to always be less than the absolute value of the nth term eventually. Okay, after some n, maybe after the 100th term or after the 5th term or maybe even after the first term, all of the terms get smaller in magnitude. That has to be true. And you need to have the nth term approach 0 in order to pass the nth term test. And again, there's a comment over there about the error bound not being tested with regard to the alternating series. So now what I have for you are examples of applying all of these tests. So take a look at this first one. Here I have a geometric series, 4 plus 8/3 plus 16/9 plus 32/27, forever like that. And I try to disguise it a little bit. But the nth term is 4 times 2/3 to the n minus 1. And one thing that I do want to point out here is the way to recognize that you have a geometric series is by the fact that you see a constant raised to the nth power, or in this case, the n minus first power. That tells you that you're looking at a geometric series. And so this is a geometric series with a ratio of 2/3. That's less than 1. And in fact, that'll tell us that not only that the series converges because 2/3 is less than 1, but it tells you what the series converges to. You take the first term, R4, and divide by 1 minus the common ratio. Now compare that to this other example where we have 2 minus 2 plus 2 minus 2 forever like that. Well, that is also a geometric series. -1 to the n minus 1, so I see a constant to the nth power again. See, in geometric, that's the only thing that happens to n, is that it's the exponent on a constant in the nth term. And that tells me I have a geometric series, but the common ratio here is -1. And because the common ratio is not between strictly -1 and 1, we say this series diverges. Here's an example, a couple of examples for the P series and the harmonic series. The harmonic series is actually just a special P series with P equal to 1. Okay, so sigma 1 over n to the P with P greater than 0 is called a P series. So and all you need to check is what's P. If P is a number that's less than or equal to 1, then we have a divergent series. And if we have p greater than 1, we have a convergent series. And so in the first case where I have the harmonic, p equal to 1 right here, I have a divergent series. And the sum of the reciprocals of the square roots of the integers, 1 plus 1 over radical 2 plus 1 over radical 3, forever like that, that series also diverges because p is equal to a half. Okay, and scrolling down a little bit, each of these series converges because each of these series is a p series with p greater than 1. And there's actually typos on both of these down here where I have sigma 1 over n here. I really wanted sigma 1 over n to the 4th. So there's supposed to be a little 4 exponent right here, and it looks like there's supposed to be a little 3/2 exponent right there. Sorry for the scratch, but you can see what the nth terms are. Both of those series converge because they're p series with p greater than 1. That's all you have to say when you recognize a p series to show that they converge. Okay, here's the ratio test. So here's a series x to the n over n factorial is the nth term. And we want to see when does this series converge. So we apply the ratio test, which means we take the limit as n approaches infinity of the absolute value of the ratio of the n plus first to the nth term. Essentially, you're looking at what is the eventual ratio of the n plus first to the nth term. And it turns out in this one, when all the smoke clears, we find a sub n plus 1 by substituting n plus 1 for n in the nth term right here. And so we get this numerator. And we just take the nth term, put that in the denominator, simplify. All the fun starts here because so much stuff cancels here. I used to love doing this when I was a student because I love to see all this big ugly mess suddenly disappear into something that was really simple. All the factors of x cancel out except for 1. We get x to the first divided by, and all the factors from n all the way down to 1 divide out, and we left with an n plus 1 in the denominator. And so we wind up with the limit at infinity. Notice that n is the variable going to infinity here. We don't care about the x. And no matter what x is, because x is some number, x over n plus 1 is going to go to 0 as n goes to infinity. And since 0 is less than 1, this series converges no matter what x is. Okay, so no matter, you put any number, any constant in there for x, and you will have a convergent series. And finally, the alternating series test. Right after this one, I'm going to give you guys, we're going to go through a couple of problems, and then I'll give you some to do also. So here's the alternating series test. What do you need? You need those 3 conditions. You need the nth term to go to 0, you need the terms to alternate, and you need the magnitude of the terms to be decreasing. And so in this case, 1 over radical n times negative 1 to the n plus 1, that series converges. We know that the nth term goes to 0. The terms definitely alternate in sign with this negative 1 to the n plus 1. And because 1 over radical n plus 1 is less than 1 over radical n for all n greater than 0, the series meets all 3 conditions of the alternating series test, and therefore the series converges. So what we're going to do is look at problems in your packet. You can get ready in your packet. We're going to look at 2 and 14 first. And then these other problems we're not going to go through in the order they're presented in your packet, but in a different kind of order because I felt that this order was a little more natural. So we're going to look at number 2 first. If we finish looking at a problem, you know, and you're still working on, you're done with one and we're still waiting, you can go and try to see if you can do the problem another way, or thinking about it a little bit harder, see if you can use your calculator on it, see if there's another problem you can do, and so on. So this first question, which of these series converges? So I look at this first series and I see sigma 1 over n squared. This looks a lot like a p series, with p equals 2, which is bigger than 1, which tells me, yes, that one converges. Roman numeral 2 looks like another p series with p equal to 1. This is the harmonic series. It diverges. And then this guy, well, again, I see this looks awfully much like a geometric series. Okay, you could rewrite this as negative 1 over 3 to the quantity n minus 1. That is, subtracting 2 from that numerator's exponent isn't going to change the series in any way. So this is a geometric series with a common ratio of -1/3, which is less than 1. So this guy is geometric. -1/3 is R, and that's less than 1 in absolute value. And so that converges. So Roman numeral 1 and Roman numeral 3, the answer is going to be C. Going on to number, here's the answer that's in your packet, I think, or your teacher will have the answers to these things in a packet. Tells you exactly the same thing I just did. So here's the next one, number 14. Which of the following series converges for all real numbers x? So we might want to think about either how fast do the terms grow, or what will happen with the ratio test. And these are the kind of problems where if you've done a lot of them, you get sort of a seat of the pants feel for how fast things grow. So I'll let you think about this one for just a minute, and then we'll look at the solution. I'm just going to give you just a brief time to think about this one. Which of these do you think converges for all real numbers x? You could substitute a value for x like 1, and it might tell you exactly the answer to which one converges. Just pick a value for x like 1, which will simplify a great deal. This guy will be the harmonic. No way. This guy is a p series with p equals 1/2. Way. Okay, this guy has e to the n over n factorial. E to the n over n factorial. Well, that might have a chance. Okay. This one, if x is too big, like 2 or 3 or 4, I think this, I haven't resolved yet because it has to be for all x. So 2 to the n over n squared, 2 to the n is going to outgrow n squared. And this one's going to actually fail the nth term test. N factorials grow faster than exponentials. And so this guy is going to fail also. And I think the answer is going to wind up being D. And the reason is that factorials really grow faster than exponentials. That's one of those rate of growth things that even the AB student should be familiar with. So I think the answer to this one is going to be D. Okay. Let x equals 1 to eliminate A and C quickly by the P-series test. And then they applied the ratio test to D. You don't actually, because it's a multiple choice problem, if you have that seat of the pants feel, you're just going to go ahead and run with the problem. Okay, so now what I'm going to ask you to do, I'm going to give you just a minute to do the next problem that I have here, which is number 16. Okay, and I have a little counter here, a little clock that I'm going to run. I'm going to give you about 1.5 minutes, work problem, come up with your answer. And I think Aaron is going to put up a poll for us. So once you have your answer, you can enter it into the poll. Okay, we've run out of time. It looks like we have a couple of votes for answer C, that P has to be bigger than a half and less than 2. Why less than 2? Well, less than 2 because this guy here is a geometric series. And so for that series to converge, we need the common ratio P over 2 has to be less than 1 in absolute value, which means P has to be less than 2. This one looks an awful lot like a P series. And so that means 2P has to be bigger than 1, P greater than a half. Let's look at the answer. And so indeed the answer is C. So you had to recognize the P series. The P series n to the 2P is a P series with the power of 2P. And the second one, you have to recognize a geometric series, a constant raised to the nth power. That constant just happened to have a P in it, so they could talk about P in both problems, okay? Okay, so if you have a question about any of these, feel free to type your question into the chat, and then either Aaron or Michael will alert me, and I can address your questions. So let's move on to the next one. This one is number 20. And again, I'm going to start a clock for you, give you 90 seconds to work this one. This one might be a little bit faster if you can recognize it right off the bat. Again, I see a constant to the nth power. So then it just becomes a matter of, well, and there's only one type of series that you know what the series converges to. This thing, and that's in this case, in the case this year, will be geometric series. Now, again, this exam isn't going to have any multiple choice problems on it, obviously, but these problems are still good to help you to review the content that could be assessed in a free response context. So let's go ahead and look at the solution to this one. So this is a geometric series with a first term. You can get the first term by substituting n equals 1 into the nth term. So if you put n equals 1 into the nth term, you get 2 to the second, 4 divided by 3 to the first. So this is A1, and so we wind up with 4/3. The common ratio is 2/3, and so the sum is the first term divided by 1 minus the common ratio. It's definitely a good thing to have memorized that formula for the sum of an infinite geometric series when it does converge. It always converges to the first term divided by 1 minus the common ratio. So here's my first term, 4/3, divided by 1 minus my common ratio, 2/3. Okay, and you simplify that, you wind up with 4. The answer is C. Okay, the next problem we're going to do is number 13, the multiple choice. And I guess I didn't put the clock on this one. I'll give you again about 90 seconds, see what sense you can make of one. They give you they tell you to use the ratio test. So they want you to jump out and use the ratio test. So you're going to take the limit at infinity of the n plus first to the nth term. Then they say, what's the inequality that you'll get that will tell you that the series converges? So you have to see what stuff cancels, how things get simplified. Okay, let's go on and look at the solution for this one. So when you apply the ratio test, you take the limit of the ratio of the n plus first to the nth term. The person that wrote this solution left off the absolute values around this test. That's okay because all these every term is positive. So that's why they did not bother including the absolute values. Notice all the stuff that cancels. The e to the n plus 1 divided by e to the n just leaves you with e right here in the numerator. And n plus 1 factorial divided by n factorial in the denominators, just everything cancels except n plus 1. So we wind up with e over n plus 1. And that's the inequality. We need that to be less than 1. Of course, it is less than 1. That limit is 0. Okay, so this series definitely converges. Okay. I think we have a couple of more of these to look at. Let's look at this one. This one asks you for all the values of x for which this series converges. This is number 15, so go to your packet if you need to. You could just look at it right here. I'll start the clock, and we'll look at this one. I hope we're having fun already. I know I am. I love doing this stuff. I like math. So this is another one where a lot of these problems are of a nature where being able to sort of acclimate yourself or orient yourself into the kind of question that you're looking at. What type of series am I looking at? Which of these 4 tests should I be thinking about? Knowing that much gets you such a good start on these problems. So again, on this one, I think I see a constant, well, a constant with respect to n, at least, raised to the nth power. 2 over x squared plus 1 is raised to the nth. And so this tells you have a geometric series, right? And so since we have a geometric series, we need that stuff raised to the n, which is the common ratio, to be an absolute value less than 1. So when is 2 over x squared plus 1 less than 1? And I think that'll happen as long as x squared plus 1 is bigger than 2. As long as x squared is bigger than 1. I'm sorry, less than 2 over x squared plus 1 has to be an absolute value less than 1, right? So x squared plus 1 bigger than 2 and x squared bigger than 1, or absolute value of x bigger than 1, x bigger than 1 and less than -1 is the answer. So again, any question you might have, feel free to type it into the chat and we'll answer it for you. Otherwise, we're going to go on to one more. I think this is the last multiple choice for you. This is talks about a Maclaurin series. So this is the first time you've seen those words. So a Maclaurin series actually refers to a special kind of Taylor polynomial, which we're going to be looking at in the second part of this session. If you want to know the value of f of 3, you just replace x with 3 and then see what you can make of it. So I'm going to start the clock again. Take a look at this one. So this is number 19 now.
Our polling is lagging a little behind, but bear with it. We'll get up here in a second.
Okay. Oh, I'm going faster than your poll. Yeah, I want to make sure that we have enough time to look at the Taylor polynomial stuff. So do enough work with these 4 tests in this first part of our session, and then we'll spend the rest of the time on Taylor polynomials. I don't want to give anything short change. So let's take a look at this one. So this is a geometric series because I see a constant in n raised, a constant with respect to n, I guess I should have said, raised to the nth power. So we need that constant again. Well, we plug in a 3 and we get a constant ratio. So negative 3/4. And so let me move on to the next, see if I can't move on to the next slide here. Let me try. So bear with me for just a second here. Okay, so we plug in 3 into our f of x and we get negative 3/4 to the n. When n is 0, the first term is 1, common ratio of negative 3/4. So what we're doing is evaluating the sum of this infinite series down here at the bottom with a1 equal to 1 and a common ratio of negative 3/4. You do all the simplification and you wind up with an answer of 4/7. So we're going to look at some free response problems next. So we're just a couple, well, actually one student sample, and here's the free response problem that we're going to look at. So they ask for a value of p such that this one series, sigma negative 1 to the n over n to the p, converges, but this other series, sigma 1 over n to the 2p, diverges. So you want one value of p such that the first series converges, but the second series diverges, and then give reasons why your value of p is correct. So you want to think about, again, where am I? What am I looking at? What is the context that I'm in? And I hope it's clear from what we've done so far that this guy is a p series. And so for that thing to diverge, we need 2p to be less than 1, which means p has to be less than 1/2. And then for this guy to converge, I think all you need is any p greater than 0. It'll pass the alternating series test. So let's look and see if I got this right. So the p that we pick had to be any number between 0 and 1/2, and actually could have been equal to 1/2, because if 2p is equal to 1, we would have had a harmonic series, and that would have diverged also. So the student who answered this had to pick any p between 0 and 2.5, and then explain why. So that was 1 point. The first point was for having a correct value of p. Another point you got for the reason why that first series converges. And this AST, what they mean there is by the alternating series test. And then why does this other series diverge for that same value of p? And it's going to be a p series with p less than 1. Well, I should say 2p less than or equal to 1. Okay, so those are the 3 points that were available here. And what we want to do now is look at some student work and see how you would grade each of these students. Okay, did this student earn 0, 1, 2, or 3 points? So take about 30 seconds, read this student's answer, and decide on how many points you think that this student deserves. Notice right off the bat, this student has told us the value of p. So talking about p equals 1/3. So you'll ask yourself, will they get that point for p equals 1/3? All they need is a p that's between 0 and 1/2. That's looking pretty good. And then they talk about similarity to the alternating harmonic series and divergent P series since P less than 1. So let's see what we think about that. That student earned 2 points. That P less than 1 was problematic because really what they needed to show that that was a divergent series was that not that their P was less than 1, but that their 2P, 2/3, was less than 1. So that student only earned the first 2 points. Take a look at this student in part D. Well, we'll take a look at part D first, and then we'll look at a student's work. Give a value of P such that this first series, sigma 1 over n to the P, diverges, but this other series, sigma 1 over n to the 2P, converges. And again, give reasons why your value of P is correct. So very similar to what we saw before, except they use different sort of constants in front of the P. So here is just a plain old P series. We need P to be less than or equal to 1 to get a divergent series. And then we need 2P to be greater than 1, converge. And so the P's that'll work on this will be any P that's between 1/2 and up to and including 1. So again, the student had to pick a correct value of P, explain why the first series diverges, and explain why the second series converges. So here's a piece of student's work. Take 30 seconds, see what you think for how many points this student should get. So this student right off the bat is picking a P of 1. And so that certainly is a number that's between, well, it's a number that satisfies what the criteria are for the first point. So the student ought to earn the first point because of their value of P. Then they say that they have a divergent harmonic series for the first case and a convergent P series for the second case. Okay, so what do we think? That student earned all 3 points. So we allowed them to say P greater than 1 down here to get that point. Okay, so that takes us to the end of that first bit of work on convergence of series. Again, I think it's pretty likely you're going to see some problem on the exam this year. So the second sort of block that we're going to look at has to do with Taylor polynomial approximations of functions. This is really it's really a different sort of a topic from series, although Taylor series and convergence of series belong together. Taylor series is not a topic that's going to be tested this year. And so that's one reason why these two are in the same sort of session this year. But Taylor polynomials are really finite series. I mean, a Taylor series goes on forever. A Taylor polynomial is finite. It's just a polynomial with finite degree. So what do you have to know about? Well, you have to know about finding a Taylor polynomial approximation to a function. And here's all this non-nested series stuff again. And you notice at the bottom here that Taylor and Maclaurin series and power series are things that are not tested. Radius and interval of convergence are not tested. And those things from earlier that we mentioned in the previous session are not tested. So just Taylor polynomials. You have to be able to compute Taylor polynomials, construct and use Taylor polynomials. That's it. Okay, so what is a Taylor polynomial? How do you construct a Taylor polynomial? And the answer to that really appears right here. Taylor polynomials provide a way to find a polynomial, quote, lookalike to a non-polynomial function. This is done by a specific formula which you should memorize. So there's actually an error in this slide right here. There should actually be an approximately equal right there. F of x is not equal to that polynomial, okay? F of x is approximated by that polynomial, usually for values of x that are close to the value of a, okay? So when a equals 0, that's a special kind of polynomial, Taylor polynomial called a Maclaurin polynomial. When we make the function out and all the derivatives agree at x equals 0, we call that a Maclaurin polynomial, the center point of the polynomial, okay? So here's an example of finding a Taylor polynomial for a particular function, cosine x at equals pi. What do I need to do in order to construct a Taylor polynomial? I don't think they're going to ask you to do something like this in particular on the exam, but this just illustrates the process and what you need to do with a specific function. If a problem like this appears on the exam, they're not going to give you a specific function. The reason is that machines, computer algebra systems, calculators, can produce Taylor polynomials. And so some students that have such a calculator could crank them out by pressing buttons. Instead, if they're going to test you on this knowledge, it's going to be from graphs and tables where you have a general function. You won't have a definition like f of x equals cosine x. Instead, they might give you a table. Here's some inputs and here's some derivative outputs for a particular function, and construct the polynomial from that table of values of inputs and outputs. And I think you'll see examples that are like that in some of the questions we're going to look at. So what do I need to do to construct a polynomial? I need to know the value of the function at the point where I'm making the polynomial. I need to know the value of the function's derivative at the point where I'm making the polynomial. I need to know the second derivative, the third derivative, the fourth derivative, as many derivatives as the degree of the Taylor polynomial that I'm asked for. Here we're asked for the fourth degree. I'm going to need the first four derivatives evaluated at this center point, x equals pi. So I've done that work for you here. Once I have those first four derivatives, I plug into that formula that I showed you on the previous page. So what makes the Taylor polynomial what it is? Well, its output and the output from the Taylor polynomial and the output from the first four derivatives of the Taylor polynomial are the same number at the center point. In other words, you plug in pi into P4 of x, you plug pi in for x, and you get -1 because these other two terms are going to be 0. And you get -1. Well, that's f of pi. If you were to plug in pi into first derivative of P4 of x, what you'll find out is that you get 0 because that first derivative is going to have 2 times x minus pi in it, divided by 2 factorial, and then x minus pi to the third power times 4 over 4 factorial. You put in pi, you're going to get 0. And if you take the second derivative, you'll see that you get a 1 for the second derivative, and so on down the line. In other words, the behavior of the Taylor polynomial and the behavior of the function at x equals pi up to the first four derivatives all agree. Okay? So here's a multiple choice problem. Okay, so remember that formula, or turn your handout to that formula for how to construct a Taylor polynomial, and then take a minute and see if you can answer this question. Okay, and we'll start the clock. And I think Aaron has another poll for us to see your answers to this one.
Hopefully this one works. Fingers crossed.
Say that again.
Fingers crossed. I think it should work. We'll see.
Okay. I guess I scrolled up too far to.
There we go.
Okay, thanks. So notice that we're asked, they give us more information than we need in the table. And that's just to make sure that you know what to look for from the table. We know we need to look at x equals 1. And so because I'm going to look at x equals 1, all of my terms with x in them better be terms that have x minus 1 to a power. I'm centered at x equals 1. That eliminates choice A. F of 1, notice that all of the answers B, C, and D all of answers B, C, and D have F of 1 correct. We start off with a 2, okay? All of them have minus 3 times x minus 1. So I'm looking at this in my table with x equals 1. So f prime of 1 is negative 3. Negative 3 times x minus 1. And then f double prime of 1 is 3. And that's why I have 3 over, I always write this for my students, 3 over 2 factorial times x minus 1 squared. So now that eliminated choice D, because choice D doesn't have that divided by 2 in it. So now a choice between B or C. Well, what do I need in that degree 3 term? Well, I need the third derivative divided by 3 factorial. The third derivative is negative 2 from the table divided by 3 factorial. And I think that ends up being negative 1/3. So the answer is going to be B. Any question about that? If you have a question, please do type it in the chat. Otherwise, here's the solution that's your teachers will have in their packet. This problem came right out of the an old version of the course and exam description. And let's go on and do another multiple choice. Here, this one is turned on its head. It's like that previous problem just turned on its head. Here, they give you the polynomial, and then they're going to ask you, go ahead and you can construct the table. So it's like a backwards version of that last problem. So I don't know what's happening with your poll, Aaron, but
we've got one response so far.
Okay, that was to the previous problem, though, wasn't it?
No, this is a new one.
Oh, this is this one. Okay, good. Thank you.
So regardless if you are a student or teacher, feel free to send those responses in. They are anonymous, so no harm, no foul.
Okay. So one of the things I ask my students to do on multiple choice questions is to look at the options and see what do the options have in common and what do the options have that's different and how does that help me? So I would look first at the column of f of x, and I see a column of 3's all the way down, and I look at my polynomial and I see that at x equals 0 I get 3, and so I'm thinking, yeah, okay, that's the right kind of thing going on. And now I'm going to look over at the next column and I'm going to see, oh, this first one's got a -8. All the others have -4s. That's the first derivative. That means that the first derivative of the Taylor polynomial has to be equal to the first derivative of the function at 0. Well, that eliminates choice A because choice A's first derivative is -8 and the Taylor polynomial's first derivative at 0 is -4. Okay, so the answer is either B, C, or D. So then I look at the next column over, and I see the second derivative, and the second derivative of this function up here, t of x, let's see, the first derivative is going to have a 4 from this term, the second degree term is going to have a 4x, and then take a derivative again, and you're going to get a 4 out of that. So now I'm down to either, that eliminates choice B. So I'm down to either C or D, and I guess it's the third derivative that's going to tell me which of these. And so that -3, the coefficient of x cubed, had to come from the third derivative at 0 over 3 factorial. Okay, so if I just solve for the third derivative, okay, in this equation, I'd multiply both sides by 3 factorial, which is 6, and that eliminates choice D. It's -18. And I hope that was clear to you. And let's see. So this is the wrong, is this the wrong solution to the wrong problem? That's multiple choice 1. And here's multiple choice 1's explanation. And here's multiple choice 2. And then here's multiple choice 2's explanation. Sorry for that little fumble there. I was tapping on the wrong slide. Okay, so let's move on and do another one. Here's number 12 in your packet, number 1 in your hearts. Take a minute to see what you can do with this one.
Then it's 3:28 right now, Mark. So just for time purposes, I know if you need to go over a little bit, that's fine.
Okay. Yeah, I think probably we've got about another maybe 8 or 10 minutes.
We're good with 10 minutes.
If that's not too much.
If people need to leave, that's fine. We'll continue recording and post the whole thing. But if you can stick with us for another 10 minutes, that'd be great.
Okay. Yeah, it's going to take about that long. I still got another, I think there's only one more multiple choice and then one free response. It might not even be 10.
Sounds good.
Okay. I figured, Aaron, that we were going to be close to it because the fact that this is really 2 kind of blocks of content. So, and they really do need to be treated separately. I think if I was a student studying for the test, everybody, I would be kind of thinking about these 2 topics as kind of 2 different things to study. Taylor polynomials are different this year from studying the convergence of series, because Taylor series and Maclaurin series are not going to be tested. So this problem can be done faster than the last one. To find the third derivative, I'm going to look at the third degree power, the coefficient of x to the third power. That -5 had to come from the third derivative at 0 over 3 factorial. So I'm going to multiply both sides by 6 again to get the answer. And -30. I hope that makes sense to you. Okay. And let's look at one more multiple choice. Try this one. I'll start the clock again. I very carefully set the amount of time for each one of those. You notice this one was 1 minute and 12 seconds. I did extensive statistical analysis to figure out exactly how long to keep the clock on. And this is one that would be like a free response problem, I think, that could be on the exam this year. It's kind of like a table of values for derivative information, and then asking a student to construct the Taylor polynomial out of the information that's presented. And notice that your calculator does help you on this problem. And by the way, I would do the same kind of analysis that I tell my students. I'm going to look at the 2 is the same, and so f of 3 equaling 2 doesn't distinguish the answers. I'm going to look at centered about x equals 3, and that eliminates those 2 choices. The first derivative being -1, all 3 of a, b, and c will have a first derivative equal to -1 at x equals 0. The second derivative being 6, well, the coefficient of the square term comes from the second derivative at 3 divided by 2 factorial, and that needs, the second derivative is 6, and so 6 over 2 factorial is 3, not 6, and so that eliminates choice C. And that third derivative is going to distinguish between A and B. You do the exact same kind of thing that I just did with the second derivative, and it winds up that the answer is A. So that coefficient of the x cubed came from, that 2 came from 12 over 3 factorial. That is the third derivative, f triple prime of 3 over 3 factorial is 12 over 3 factorial. That's 12 over 6, and that's where that 2 right there came from. Okay, so the answer is A. Okay, now we have I think just one free response problem to look at. So, or maybe 2, we'll see. Okay, so here's the first one. We have a function having derivatives of all orders for x greater than 0. We have selected values of this function h and its first four derivatives given in the table. And they tell you that the function h and these derivatives are increasing on the interval from 1 to 3. And in part A and part B, which would be appropriate for this year, this problem also had, I think, a Lagrange error bound in it. But for part A and for part B would be appropriate this year. Find the first degree Taylor polynomial for h about x equals 2 and use it to approximate h of 1.9. Is the approximation greater or less than h of 1.9? Explain. And then write the third degree Taylor polynomial for h about x equals 2 and use it to approximate h of 1.9. And so since you're using x equals 2, we're going to be focusing our attention on row 2 in the table. See if you can take 30 seconds and see if you can write out at least just the answer to part B, just writing out the third degree Taylor polynomial. And then we'll look at those the answers to both of those questions. So here's the solution. I was laughing because they had circled that row in the table in exactly the same color that I circled it here on here, and that was totally an accident. So to get the third degree Taylor polynomial, what do? We take at x equals 2. We take h of 2, this 80 is the constant term, plus the first derivative, 128 times x minus 2, plus the second derivative divided by 2 factorial. That's where the 6 came from, was 488 over 3 divided by 2 factorial, or just divided by 2, times x minus 2 squared. So when you're constructing the nth term of a Taylor polynomial, you want to think about those 3 little components: the derivative, the x term raised to the correct power, which is the same as the power is the number of the derivative. So like when I'm on the second derivative, I should see the polynomial have a degree 2 term. Okay, so the second derivative and then x minus 2 to the second, and then all of that divided by that same number, in this case 2 factorial. So 488 over 3 divided by 2, and you could have written that way on the exam and gotten credit. And then the third degree term, 448 over 3 divided by 3 factorial, okay, divided by 6, that's where the 18 came from, times x minus 2 to the third power. Then if you use that to approximate, all you got to do to approximate the function value, you simply substitute that 1.9 in for x. And this was an open calculator question, so here you see that number actually evaluated. Up here in part A, I want to point one thing out which may help you if you haven't done a lot of work with Taylor polynomials. I would always tell my students that a Taylor polynomial is like a tangent line on steroids. So what does a tangent line have in common with a function? Well, the tangent line has the same output as the function does at the point of tangency, and the same first derivative, the same slope. Well, a Taylor polynomial, you just keep going. You don't just match up the function output and the first derivative, but you match up so that the polynomial has the same second derivative as the function at the point, the same third derivative as the function at the point. However many derivatives you want, you match up and you get the degree n Taylor polynomial matches the first n derivatives of the function. That's the key thing to understand about Taylor polynomials. And so because their behavior might agree with, the first 4 derivatives, then, or the first 3 derivatives is the case in this problem, that's why you can use a Taylor polynomial output to approximate a function output, usually near the point where that polynomial is centered. Okay, so I think what we're going to look at now is another free response problem, a function with derivatives of all the orders for which f of 2 is 7, and when n is odd, the nth derivative at x equals 2 is 0. When n is even and bigger than or equal to 2, the nth derivative is given by this ghastly thing. The nth derivative at at 2 is n minus 1 factorial, and I think that's over 3 to the n, and that got kind of smushed together there. Then they ask for the 6th degree Taylor polynomial at x equals 2, and ask for the coefficient of x minus 2 to the 2n. So this was from a problem from 2005, and it's kind of intimidating, I think, when you just look at it on its face. But it turns out that this isn't such a hard problem. They give a formula for the nth derivative, and so you can calculate any of the derivatives just by plugging in the appropriate value of n into this formula. Okay, so this is only true when n is an even number. So for n equals 2, 4, and 6, okay? When n is odd, derivative is 0. So you'll notice that in the polynomial, that's the answer here, there's no odd terms because all of the odd derivatives are 0. So there's no odd degree terms on x, okay? And then to calculate, let's say, where did they get this coefficient of x minus 2 to the 6th? Well, the 6 factorial is from the formula, the n factorial on the bottom, and then n minus 1 is 5 factorial over 3 to the 6th. This is coming from, that's the nth derivative evaluated at 2. Okay, so they just did that same thing for all of those other coefficients. And so we have some work here about grading some student work on these same problems. In the interest of time, I think all I'll do is point out what the score is for this student. So this these problems this A was worth 4 points, 2 points for the degree 1 Taylor polynomial, 1 point for substituting 1.9, and 1 point for showing that the value of the polynomial at 1.9 was smaller than the value of the function at 1.9 with an appropriate reason. And that reason was that the second derivative was positive, which meant concave. The function graph was concave up. And so if I have a concave up function, a tangent line approximation is going to give me a number that's smaller than the number that's on the function graph. Okay. So this particular student's work earned 3 of those 4 points, and the reason they didn't get the last point was because their reasoning about the behavior at x equals 2 was not sufficient to. They had to talk about the behavior of the second derivative on the interval between 1.9 and 2, not just at 2. So they lost that last point. Okay, so I'm going to jump to the end. I'm happy that you joined us. You were able to join us today. One of the things that I always ask my students to do at the end of a class is to think about what we just did and try to remember the things that stick out. What did you just learn? Reflect on the things that you learned. Try to cement those things in your memory. And the things that are highlights from what you just saw are the things that you want to focus your attention on. If you have any questions, feel free to send me a question through my email, my Gonzaga email that you see on this this last slide here. And I'll turn this back over to Aaron and to Michael. Thanks a lot for joining us today. Aaron.
Thanks, Mark. We appreciate it.
Thank you.
Yeah, again, I think what Mark had to say, you can't get much better than hearing from him. So we're very appreciative that you're able to join us for leading our session. The screen you can see.
Thanks, my pleasure.
Yeah, for sure. If you have follow-up questions, like Mark said, feel free to reach out to him or any of us here at Advanced Kentucky. We'll be happy to help you. The handouts are posted in the Google link there, as well as linked through kyap2020.com. If you need the solution handouts, feel free to email us and we will get those to you if you are a teacher. Next week, Mark is back with us again. We're lucky to have him to talk about free response strategies and mixed review. Same time, same place. So please join us. Please pass the word along to those who may have missed today. Again, today's recording will be posted to the KYAP 2020 website by the end of the day. So Mark, Michael, if you don't have any questions, we will go ahead and sign off.
Okay.
All right, everyone take care. We will see you next week.